In this video, we're going to learn to graph inequalities in two variables. So we've already seen how to solve inequalities with just a single variable. If we recall those steps, the first thing we did was we found the boundary values, and then we chose some test values. We tested those test values, and then we selected the regions that worked. We're going to do more or less the same thing with our graphing inequalities in two variables. Just now we have two variables, so we can't solve for just a sequence of numbers like we did before, where say x is greater than 1, x is less than 1. We have to actually shade in the regions that validate the inequality. So to graph our inequalities, the steps are going to look very similar. Like I said, first we're going to graph the boundary line or curve. So we're finding that boundary point, but now it's not just a point, it's a line or a curve. Second, we're going to choose and test values, same as before. And then three, we're going to select the ones that work. But to select it now, because we're not just writing down intervals, we're going to have to shade the regions that work. So let's jump right into an example. Let's graph y is less than or equal to 3x minus 2. So notice how we have two different variables here, the x and the y. If this was a y is equal to 3x minus 2, we'd all know exactly what that graph looked like. The y-intercept's negative 2, and the slope is 3, so that's saying going up 3 over 1. And this would be my line. That would be true if it was an equals to. We don't have an equals, strictly an equals to here. We have a less than equals to. So we have graphed the boundary line or curve. Now, one thing I want to note on this, number one, pay special attention to dotted or solid lines. So we're going to look at this more as we go through examples today. But if we have an equal to bar, we're going to use a solid line. If we have no equal to bar, if it's strictly y is less than 3x minus 2, we would have a dotted line. And so make sure that we are indicating that line or curve correctly with the dotted or solid line. Now I'm going to choose some test values. So let me choose a test value. We'll choose the point, because it does need to be a point. We have an x-y equation. Let's choose the point of 0, 0 first. Now, when I'm choosing test values, I'm just choosing any number on this side or any number on this side, any point on this side or any point on this side. It does not matter where it is precisely, but we want to make sure that it is definitely in that region. So, for instance, would I want to choose something like 2, 4? Well, that's going to get kind of close to the line. Why make it that close? Choose something that's definitely in that region. 0, 0 is always easy to work with. It's clearly in that upper half of the shape or the division line. So if we plug in 0, 0 less than or equal to 3 times 0 minus 2. So we get 0 is less than or equal to negative 2. Is that a true statement? Absolutely not. That is false. And so 0, 0 is not working. That already leads me to believe I need to be shading this other portion. Let me just verify that. Let me choose another test point over here somewhere, just to make sure that we have it right. It's always good to do that double check. So I'm going to choose a point 5, 0. I'm confident that is in the other half of the divisional line. So if I plug that in, I'll have 0 is less than or equal to 3 times 5 minus 2. 3 times 5 is 15, so we get a 13. 0 is less than 13, that's absolutely true. And so we have validated that this half should in fact work. So that's my version of the shading. If you had, depending on how much work you want to do, it's just got to be clear to me what you're actually shading. Do you need to test both regions? No. Once you find that one region works, the other should not. Once you find that one region does not work, the other should. But again, it is much better to test both and be certain. So I would recommend doing that. Let's take another example. So that's a linear inequality, but we can look at nonlinears as well. So let's take y is greater than x squared plus 3. If this was an equal, we would know exactly what this would look like. The x squared function, the parabola, is shifted up by 3 units. So that would be where my vertex is sitting. From there, it goes up 1 over 1. So we have to recall the transformation stuff that we did back in the very first chapter. We have the parabolic shape, but then it's shifted up by 3. And so this would be my curve. And again, the straighter you can make it, the better. The smoother, I should say. Not straight, it's not a line. But the smoother you can make it, the better. I'm trying to graph on a screen here, which is a little more challenging. So that would be our curve if it was an equal. But notice we do not have any equals here. We have y is strictly greater than x squared plus 3. So this is not correct. This is not the correct division of the line. I really need to be using a dotted line to create the division between what is acceptable and what is not. Just like before, I'm going to choose some test values. So let me choose the point 0, 0 still would be a point that's clearly on one side of this figure. If I plug in 0, 0, is 0 greater than 0 squared plus 3? Is 0 greater than 3? That's absolutely false. And so the lower region will not work. Already I'm believing that this should be the region that will work in here. But let me test that with another point. So something that's definitely in this region would be, say, something like 0, 5. If I plug in 0, 5, is 5 greater than 0 squared plus 3? Well, yes, 5 is greater than 3. That is true. So we've validated that upper region. Now, there's actually a different way to think about these. There's more of an intuitive way. So let me shrink this down for just a minute so I can view both at once. There we go. So if we think about what this is saying, this first equation is saying we want our y values to be less than the line, because this 3x minus 2 is the line, right? We want our y values to be less than the line created by 3x minus 2. So if we were to look at, say, this x value right here and go under it, that number is acceptable because it's less than. If we were to look at this, I said the wrong thing. If we were to look at this y value right here, go under it, all this stuff is acceptable. And that's giving us that lower portion of the graph. If we were to take our parabola, what we're saying is we want our y values to be greater than the parabola. So if I were to take this y value right here, I really want to be above it. And so I'm shading above. If I were to take this y value, we're shading above. So again, we can kind of see how intuitively these make sense. I would argue you never actually have to do a test value on these. They're even easier than solving the inequalities we did before. To graph these inequalities, we can purely look at and kind of make that decision. Let's take a couple more examples. Let's say we have x minus 1 squared plus y plus 3 squared is greater than or equal to 25. We should recognize this is the equation of a circle. The center of this circle would be the point 1, negative 3. We get that by reversing both the signs, 1, negative 3. And then the radius would be 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so circles are a struggle for me to draw. That's not a great job. Let me try it again. Oh, that's even worse. I should have stuck with the first. Something like that. That's good enough, I guess. So again, a little bit easier to draw when you have a formal grid in front of you and it's on a piece of paper. But what we want to be indicating is that we have gone up, down, left, right by 5 units. 1, 2, 3, 4, 5. So that would be the other side of the circle. 1, 2, 3. That's not a very good scaling. 1, 2, 3, 4, 5. So we should see that approximately hitting those points. So there's my circle. Because we have the equal to bar, we do want to include the circle. We want to have the solid circle. And so I'll do the test points in just a second, but I want to take it from the intuitive approach first to show how that works. What we're saying, we want our circle to be larger than the radius 5. We want the y values to be larger than 5, and so that means we have to be outside of this circle. Like so, everything outside. If we were to choose a test value to test that, very easy test value would be the center of the circle, 1, negative 3. Well, clearly when we plug that in, we get 0 plus 0. That's not going to work. So the inside of the circle, not going to work. That's not greater than 25. That's 0. If we were to choose something outside, I could choose maybe, say, 10, 0. So we'd have 10 minus 1 is 9. 9 squared is 81. Plus 9, 90. 90 is greater than 25, so that also works out. Let's take a look at one final one. Y is less than 2 to the x. We can do these inequalities for any type of function. Any inequalities, so less than, greater than, equal to, and any function. We just have to know how to graph the function. So 2 to the x is another function we should recognize how to graph. Any exponential always passes through the y-intercept at 1. Also has that asymptote sitting on the x-axis. And then as our x shifts over by 1, our y's will double. So we'd have 1, 2, 2, 4, negative 1 would be a half, And so we'd end up with this curve, but I need to make it a dotted curve because we do not have the equal to. So it should look something like that. If we think about the y values that we are requesting, we want our y values to be less than the curve, meaning we want to be underneath of it, under here. So I always ask this question in class and make my class think about it, because this is a video, I can't do that in the same way, but I'll kind of pose it to you. Should we graph strictly to the asymptote? Should we graph all the way through the asymptote? Should we stay under the asymptote? And the answer to that is we want to graph everything below the curve, regardless of what's happening with the asymptote, because the asymptote, all that is doing is controlling the curve itself. What we're saying is we want to be less than the curve. We don't care where the curve was controlled by, so we're passing right through that. We want everything underneath that curve. Again, we could choose that test value to test this. We could choose 0.00. That should be in the region that works. Is 0 less than 2 to the 0? Well, yes, 0 is less than 1. That checks out. And so that's how we graph our inequalities. From here, what I want to do is I want to graph systems of inequalities. So we're going to take these inequalities, put multiple ones together at the same time. We're going to look at how do we select those regions to graph. So that will be in the next video.